Okay, good morning, guys. Do you guys have any questions before we start? So today we'll talk about electromagnetic waves. Do you guys know what electromagnetic waves are? Okay. Can you, what?
Vaguely. I haven't done anything on it in a while.
Okay. What's your vague impression of electromagnetic wave?
They're kind of the waves that form from like magnetic fields that permeate out
Right.
kind of bit.
So like the name suggests,
Yeah.
these waves have both electric fields in them and magnetic fields in them. Okay. So I'll show you an example. Here's a here's an electromagnetic wave. Okay. This wave is traveling in this direction. And there's the electric field. So there's this. Okay. And here's the magnetic field. So it turns out that in these electromagnetic waves, the electric fields, the magnetic fields, and the direction of travel are perpendicular to each other. Okay. So if you use your right hand, if your thumb points in the direction of the electric field, your index finger will point in the direction of the magnetic field, and right hand. And your middle finger will point in the direction of travel. Okay. So this is what is called a plane polarized wave. The electric field oscillates like that in the direction of your thumb. The magnetic field oscillates in the direction of your index finger. Okay. And the middle finger points in the direction of travel of the wave. All right. So what are examples of electromagnetic waves?
Radio waves,
Mm-hmm.
rays,
Gamma rays,
microwaves,
microwaves,
visible light, and what?
visible light. Okay.
Violet light.
Yeah. So the fact that visible light is an electromagnetic wave was realized by Mr. Maxwell one afternoon. And we'll talk about that. Okay? So we didn't know that visible light were electromagnetic waves. All right, so let's show you examples of electromagnetic waves. Before we do that, all right, well, okay, let's. So all these guys are electromagnetic waves. Okay, so all their nature is the same. AM radio, FM radio, microwave, radar. Okay, visible light, X-rays, gamma rays. Okay, UV light. So here's the visible light. Okay, so these are all arranged in order of decreasing wavelength. Okay, so they all have the same nature. They all travel at the same speed in vacuum. Okay, and the speed at which they travel is c, and their speed is denoted by c. It's 3 times 10 to the 8 meters per second. So light would travel around the earth. This roughly works out to, it would travel around the earth 10 times in 1 second. All right, so we'll talk about an afternoon where Mr. Maxwell realized that visible light was an electromagnetic wave. Okay, so that's what we'll start off with. Okay. So anyway, this is the electromagnetic spectrum. Okay, you do have a sensor that detects some of these waves, and your sensor works in this small window. Your sensor can't see this. Your eyes are the sensor that'll see in that small window. Okay. All right, so let's see what Mr. Maxwell discovered one afternoon. Okay. So electromagnetic waves are waves that have both electric and magnetic fields, and that's why they're called that. Okay. So here are the Maxwell's equations. Okay. And they predict all phenomena. So one afternoon, Mr. Maxwell after lunch is studying these equations and wanted to see what they predict. Okay? And he's studying them in vacuum. So in vacuum, there's no charges, this term is zero. There's no currents, this term is zero. Okay? So he's studying what these equations are going to predict in vacuum. Yep. So we'll look at that. We'll come to these slides in a second. So what we're going to do is we're going to make this zero, this zero. Okay. Do you guys know what these operators are? This operator?
It's the gradient.
And that's the curl. This is the divergence. Okay. And you all familiar with these operators? Do you know what they do? Okay. What's that?
I learned them, but I already forgot.
Okay. So see, this is like the dot product. This is divergence. This operates on a vector field. Okay. So by the way, so I'm just going to write one of them. Okay. So these vector fields are functions of space and time. I plus, and now I'm not going to write. Okay. So these are vector fields. What does it do? At a given space time, for a given space point at a given time, it gives you this vector. Okay. And what a divergence of E is this. Okay. Okay, so that's that operator. Yep. Curl of E is this operator. Del by del y Ez minus del by del z Ex Ey. I plus del by del z Ex minus J plus del by del x. And again, if you know cross products, you can remember these. Okay. So this is the divergence operator operating on a vector field. This is the curl operator operating on a vector field. Okay. So those are the two operators. And you will talk about, you'll need the gradient operator as well. Well, the gradient operator acts on a scalar field, and that's equal to del phi by del x I plus del phi by del y j. Yeah. All right, so this was just a reminder of all those operators. Okay. Okay, now what we'll see is what did Mr. Maxwell, he was playing around with these four equations. Okay. We call them Maxwell's equations now, and we'll see what they predict. Okay. All right, so here's a vector identity. What is this saying? So this is a vector field. You know what is a vector field again? A vector field is it associates a vector at every point. Okay? So think of a field and a corn stalk. Think of that as a vector. Okay? So that's a vector field. Okay. What this is saying is, if you take the curl of a vector field, that is equal to gradient of the divergence. Okay. This is a scalar, and gradient of a scalar we just saw is that. gradient of a scalar is that? Oh. Minus del square A. The del square operator is the following. A just means the following. Del square del x square A plus del square del y square A. Okay, that's what that is. All right, so what we're going to do is, this is a vector identity. You'll learn this in Calculus 3. Okay. What does an identity mean? It applies to every vector field. It's true for every vector field. So of course it's going to be true for an electric field as well. Okay, so let's apply that to an electric field. What are we studying? We're studying electric fields in vacuum. All right, so we're going to apply this to a vector field. Curl of E, okay, is equal to, so curl of E is equal to gradient of divergence of E. Well, okay, I'll write this. Gradient of divergence of E minus del square E. Okay, what are we studying? We are studying fields in vacuum, E and B in vacuum. In vacuum, we saw that what is divergence of E? 0. Okay? So this term is 0 and this term is 0. Okay? All right. What's on the right hand side? Okay. Curl of E is del B by del T. So on the right hand side, so then curl minus del B by del T. See, curl of E was del B by del T. Okay. So this fellow is equal to that. Now, this is a derivative with respect to x, and this is a derivative with respect to t. So you can switch them around, switch their order. Okay. So this is equal to minus del by del t, curl of B. So this is Maxwell having coffee in the afternoon. What is curl of B? It's epsilon naught mu naught del E by del T. So this is equal to del by del T. Curl of B is epsilon naught mu naught del E by del T. Okay, so what we have here is this is equal to that. I hope you followed all of that. All right, now we'll make these pluses. Okay. So, all right, actually I'll copy this. So we are here. Okay. So what we have is, this is what Mr. Maxwell found. Okay, those 4 equations predicted this. Okay, by the way, the speed of light was measured, let's say about 50, 60 years before Mr. Maxwell was playing around with these equations. Yeah, so he knew the speed of light. All right, so let's look at what these equations predict. Okay, so you got this equation, and I'm going to grab this guy. All right, so a couple of things about this differential equation. What does this mean? Del square del x square plus del square del y square plus del square del z square e to the power x, y, z, t equal to epsilon naught mu naught del square e by del t square. And again, E is I didn't write it here, but E is a function of x, y, and z and t. So if electric fields exist in vacuum, they should satisfy this differential equation. Yep. So by the way, so this looks pretty messy. Okay. What this is relating is, see, these are all spatial derivatives. See, these are E changing with respect to x and so on. And it's relating it to E changing with time. Spatial derivatives are related to the field's time derivatives. Okay. Now, the units of E are volt per meter. Okay. So about an equation, you know that whatever are the units on the left-hand side, you have to have the same units on the right-hand side. Okay. So this is electric field units divided by distance square units. Z is a distance, X is a distance. So electric field units, distance square. Well, this is time square. So that must means that this is the velocity. So epsilon naught mu naught must mean it's a velocity square. Okay. Now these were constants that were known, and you could calculate that, and this turned out to be the speed of light. All right. So that's when Mr. Maxwell realized that light is a form of electromagnetic wave. Yeah. All right, I jumped a step, but I hope you're understanding some of this stuff. This is a pretty neat discovery. A very neat discovery. All right, now before we do this, so Maxwell did the following. Okay. Now, how do you eat a steak? One bite at a time. Okay, so we're going to do that. Okay, so this is the differential equation, and you want to solve this. Well, we're not going to solve the most complicated thing. Let's consider the case where E is only a function of x and t. Okay, you need a spatial dependence and you need a time dependence. So we're going to consider a case where E is dependent only on x and t. So this term will drop out, this term will drop out. Okay? So del square by del x square E x t. And now I've dropped the vector sign. And remember, so this was the speed of light. So that's c square del square E by del. Again, so this is the wave equation. You will encounter this quite a few times. A wave equation involves the second order spatial derivative and the second order time derivative. Okay. So it's relating the second order spatial derivative to the second order time derivative. Now this is very easy to solve. So if electric fields and magnetic fields exist in vacuum, an electric field of this form must exist in vacuum. So we'll call this the amplitude E naught cosine kx minus omega t. So this solution exists in vacuum, where omega by k is equal to the speed of light. This is equal to that c. And that is this guy. That is this guy. So there is the amplitude and there is the cosine function. Yep. And this wave travels at the speed of light. So Mr. Maxwell realized one afternoon that light was an electromagnetic wave. I didn't show you the other half. The magnetic field has the exact same equation. Wave equation satisfies the exact same equation. And since E and B field are related, E and B field are related by these equations, E and B fields are related like that, it turns out that, so there is the wave equation for the electric field. You get the exact same equation for the magnetic field. And since E and B fields are related like that, if you consider, so we'll consider plane waves. Okay. When we say plane waves, what we're saying is, so there's the direction of travel. The E field is this constant in this plane, in a plane perpendicular to the x direction. So what this field is xt. When we consider that simple kind of field, what that is in this plane on a plane that's parallel to the YZ plane, the electric field is the same everywhere. Okay, so that's what this means. So here is a wall of constant electric field. Yep. All right, so we'll consider plane traveling waves, which are these. Electric and magnetic fields are perpendicular to each other and to the direction of travel. Electric and magnetic fields are perpendicular to each other and to the direction of travel. Okay. So we're looking at solutions where E is only a function of x and t. Okay. Similarly, B is only a function of x and t. Okay. And the solutions to these differential equations, wave equations, okay. So C is the speed of light, are these guys. So there is E max times cosine kx minus omega t, and B is B max times cosine kx minus omega t. Okay, so here is the E and B field. And these two equations show you that they'll be perpendicular to each other. Okay. So if E is in the x direction, B will be if E is in the z direction, B will be in the y direction, and x direction is the direction of travel. Okay. So there are the solutions. Okay. And these are traveling waves. Okay, so here's a sine wave traveling in that direction. All right, so again, we did a lot of stuff, so let me make sure that let me summarize it very simply. Okay, so what was Mr. Maxwell doing? Maxwell was playing with those four equations one afternoon in vacuum. What did he find? He found traveling wave solutions. solutions which contain both E and B fields. And these traveling wave solutions were traveling at
It's beautiful.
speed of light. So that afternoon is when we realized light was an electromagnetic wave. That's the nature of light. Okay. And then eventually we realized that there are all different kinds of electromagnetic waves. Okay. So with different wavelengths, and the wavelengths is the longer the wavelength, the redder the light appears in that small window for us. Okay. Today we know that light comes in packets. All electromagnetic waves come in packets. This is the quantum description, and this is called a photon. You can have a photon of every kind: X-ray photons, gamma ray photons, light photons. Okay? And the energy of this photon is h, the Planck's constant, times the frequency. All right. The plane in which the electric field oscillates, so this is the plane in which the electric field is oscillating. That is called the plane of polarization. Okay. So your sunglasses, they're Polaroid sunglasses. Do you know what they do?
They have a bunch of bars that block out some of the sunlight.
Okay. So sunlight has all polarizations. Okay. Sunlight has this polarization, meaning the electric field is oscillating like that. It has this polarization, every polarization. Okay. So those sunglasses are designed to let through this polarization, and they absorb this polarization. So even if you had clear polarized sunglasses, clear, absolutely clear, here's sunlight coming, only this polarization gets through, this gets absorbed. So every polarization can be divided into this and that polarization. So even if you had clear glasses, the intensity would be half. So here's a beam of sunlight getting at you. Here's a Polaroid sunglass, even clear sunglasses, and what gets out is I naught by 2. So the intensity is half. Okay.
So why is it that with the sunglasses, like some of the bars are this way and the other lens they're this way?
Oh, you lived in Colorado? So how do you know that?
Because I have glasses that do that, my sunglasses do that. I got them from a thrift store, so I guess whatever.
All right, so here,
But when I rotate them, like when I'm looking at a phone screen or at something,
Mhm.
I rotate it,
Mhm.
one glass gets clear and the other one gets foggy, and then I do it the other way, and one gets clear and the other one gets foggy.
no. So you're doing it with 2 sunglasses.
No, same.
All right.
One lens is rotated, one lens is.
All right, so I'll tell you in a second, so we're coming to that. So for clear Polaroid glasses, again, the intensity is half. In addition, so when light reflects off of the ground or a lake or something, this is the preferred polarization. There's more of this light than this light. So if you're wearing sunglasses, the glare is cut off. Okay? So if you're in Florida, this polarization is reflected, and you want to cut off that glare, and so you wear polarizers that let through this light. What if you're living in Colorado and skiing? This polarization gets reflected. Okay, so you want to cut off that glare. So there in the mountains, you're buying Polaroids that are letting through this polarization,
That makes sense.
and that's what you buy.
Because
And
my ski goggles are polarized in the other direction.
yeah, that's right.
What?
You're right. There you go.
How do you know?
But go ahead.
How can you tell like which way they're polarized?
Well-
My mother, her phone screen is polarized, so whenever she has her polarized sunglasses on, she can't look at her phone screen because it's rotated in the wrong way.
Okay.
That's
And so I put the glasses in front of it and I rotate them, I can see what way the sunglasses are polarized.
Well, also, if you take one that works in Colorado and one that works in Florida, you look through both of them and they'll be dark. They're cross-folded. All right, so that is called the plane of polarization. So let's make sure. So the plane in which the electric field oscillates. Okay, so again, I guess that was a better picture. Okay, so the plane in which the electric field oscillates is called the plane of polarization. Okay. So K is the wave number, which is 2 pi divided by lambda. Omega is the angular frequency, 2 pi times linear frequency, and the energy of the photon is HF. So higher the frequency, higher the energy of the photon. Okay, so let's look at this in the electromagnetic spectrum. And you can see that gamma rays have the highest frequency. Okay, so these are the higher frequencies. Okay, and they have the highest energy, and then X-rays are that, and so on. So this is arranged in, so C, the speed of light is frequency times wavelength. Higher the frequency, lower the wavelength. Okay, so here's the higher frequency, and these have wavelengths of 10 to the minus 12 meters. Okay. Now, here's the thing. Let's say if you want to see this object, so if you want to see an object, what do you need to see this object?
Light needs to reflect off of it.
Or the light needs to reflect off of it. Okay, now if you want to see this object, if you use a light whose wavelength is that, you can't see this object. Okay, so if this is the object you want to see, and you use a light of this wavelength, you can't see it. Well, what do you have to do to see this?
Put a bunch of other wavelengths.
You have to use a wavelength who's shorter than the dimension of that. All right, so since I can't draw that, okay, you have to use a light of wavelengths either that size or smaller. Okay, so if to see that, you have to use a wavelength equal to or smaller than that. Okay. With a smaller wavelength, you can see stuff. Okay, so if you want to see a molecule or an atom, you need to use light of wavelength 10 to the minus 10 meters or smaller. Okay, so if you wanted to see atoms, you need to use X-rays. Okay, so you guys have heard of X-ray diffraction, so you know that's what's happening. All right, so and so on. Okay. All right, now let me start from the beginning. I've been all over, but I'm going to quickly go over the slides again. Okay. Do you guys have any questions before we get into this? Okay. So these are the 4 equations that describe all electromagnetic phenomenon. Mr. Maxwell was studying these equations, and he wanted to study what kind of stuff can you see in vacuum. So this is set to 0, this is set to 0. So he studied those 4 equations and was seeing what they predicted. Okay. So when you produce electric and magnetic fields, this equation just tells you what the effect of the electric and magnetic field is on charges. Okay, that's the Lorentz force equation. The magnetic field exerts a charge force on a moving charge. Electric field exerts on any charged particle. Okay. we'll come to these slides. We won't worry about these slides. Okay. All right, I'll tell you what this is telling you. So what this guy is telling you is, so if you increase the magnetic field, okay, so if magnetic fields increase, if magnetic fields are time varying, they will produce electric fields like that. The further out you are, the weaker the electric fields. Okay, so this is what this equation is telling you. Time varying magnetic fields are producing electric fields. And the form of the equation tells you that if a magnetic field is increasing in this direction, that's the direction in which the electric field is produced. Okay, so this is predicted by this equation. Yeah. So the important thing for us is time varying magnetic fields are producing electric fields. Okay. And is the converse true? Is time varying electric fields, will they produce magnetic fields? They do indeed. And that's what this equation is telling you. Time varying electric fields are producing magnetic fields. Okay. So that's the next slide. So if you increase the electric field in this direction, it produces a magnetic field and like that. Okay. How do you increase an electric field like this? Can you think of a way to increase the electric fields?
Charging a capacitor?
Very good, my friend. Very good. Okay. So if you're charging a capacitor, as the charge builds up, the electric field there increases. Okay. And so as the capacitor is being charged, as the electric field is increasing, there will be a magnetic field, concentric magnetic fields around the plates like that. All right, so for our purposes, what we need to know is time varying magnetic fields give rise to electric fields, and time varying electric fields give rise to magnetic fields. Okay, so that's something we need to keep in mind. Okay, well, why is that important? Remember, for electromagnetic waves, what is happening? So if you're standing right there, let's say you're standing here, this electric field is changing as it's oscillating, and this magnetic field is oscillating as well. And those magnetic fields, oscillating magnetic fields, are producing the electric field, and the oscillating electric fields are producing the magnetic fields, okay, which is propagating a bit. All right. Anyway, so that's what these two slides tell you. Okay. So Mr. Maxwell is going to study these equations in vacuum. This guy is 0, this guy is 0. Okay, so using this identity all in one afternoon, remember? Using this identity, he applies that to the 4 equations and he gets this equation for the electric field. So what does this equation tell you? That an electric field in vacuum must satisfy this differential equation. This is called a wave equation now, today, because it's predicting wave solutions. Okay? It's called a wave equation, and it's relating the second order spatial derivative to second order time derivative. Okay? And this is the velocity of the propagating wave. I guess C is the velocity of the propagating wave. Okay, so magnetic fields satisfy a similar equation, exactly same equation. All right, so of course this involves X, Y, and Z. So what is it that we're going to do? We're going to look at the simplest solutions to this equation. We're going to look at solutions that depend only on X and T. Okay. All right, and so we're going to look at solutions that only involve X and T, and so those wave equations reduce to that. And here are the solutions. Okay, E, so you have sine and cosine wave solutions. There's the amplitude of the wave, there's the wave number, and that's the angular frequency. Okay, and these solutions, and if E is in the Y direction, B is in the Z direction. And these guys look like this. So the electric field is like that, the magnetic field is like that, and that is the direction of propagation. Okay. So these solutions were predicted by those equations. Okay. And so Maxwell predicted these propagating solutions, and all waves carry energy. We knew that. Yeah. So when somebody predicts something, you want to go test it out. Okay. And Mr. Hertz tested this prediction out. And here is his setup. Okay. And that's why we named that unit for frequency after Mr. Hertz. Okay. All right, so what is this setup? And there is a picture of his equipment, but here's what this is. Okay. Now, let me tell you one more thing. How do you produce electromagnetic waves? To produce any kind of wave, electromagnetic wave, what you need to do is you need to make a charge accelerate. You need to accelerate a charge. Okay. You want to produce gravitational waves, you have to accelerate a mass. Okay. How do you accelerate? What's the most convenient way of accelerating an object? You grab hold of it and you jiggle it. So you grab hold of it and jiggle it back and forth. And this will accelerate, and what you find is it'll emit electromagnetic waves like that. So here's the setup. Here is the charge jiggling. Okay, so we want to make a charge jiggle. Okay. So here is a capacitor and here is a inductor. What do a capacitor and an inductor do?
Oscillate.
They oscillate. Okay, they oscillate. But since you have resistors, that oscillation would die out. So you keep pumping energy. Okay, so it's like you push a child on a swing, and if you're not pushing the child anymore, what will happen? The swing will stop, and the child will cry. So you got to keep pushing. All right. So this thing is oscillating. We'll couple this via transformer to another thing. And if you have two pieces of metal, what is that? That's a capacitor. Okay. So this is coupled to there and their frequency matches, so this will oscillate. Well, this becomes positive, negative, and then in the next cycle this is negative, positive. It's like jiggling a charge. Okay, as the charge on the capacitor oscillates, it's like jiggling a charge. And this will emit electromagnetic waves. Okay, that Mr. Maxwell predicted. And if this carries energy, you make this electromagnetic wave. So this is another tuner, another circuit just like that. And a wave carrying energy should excite. If the frequency matches the frequency of this oscillator, it should set up large amplitude currents in this guy. And that'll show up as a spark there. So for the first time, you were able to transmit energy wirelessly. This was the first wireless communication. Okay. Well, we have been doing it without realizing it. So you can use a lamp and, use Morse code, and that's wireless communication as well. But we didn't know the nature of light and all that kind of stuff. All right, so some properties of electromagnetic waves. We'll talk about plane waves. What do we mean by plane waves? So the electric field is constant on this plane. Everywhere it has the same value. Everywhere on this plane, it has this value. Everywhere on this plane, it is 0. And right now, this is just a snapshot. At each location, the field varies, okay? So That's the wavelength of light. Okay. At any given location, for a plane wave, the ratio of the electric field to the magnetic field is equal to that, the speed of light. Okay. So at every instant, the ratio of E and B field is constant and equal to the speed of light. Both E and B satisfy the wave equation. Okay, so the wave equation was del square E equal to 1 over C square del square. Okay. And we consider the simplified form of that for X E depending only on X and T. So what is the signature of a wave equation? It relates the second order spatial derivative to the second order time derivative. Okay. That's the wave equation. Both E and B satisfy wave equation. Electromagnetic waves travel in vacuum. Remember, we were solving them in vacuum at 3 times 10 to the 8 meters per second. Okay. E and B fields are perpendicular to each other and are perpendicular to each other and to the direction of propagation. They're perpendicular to each other and to the direction of travel. They obey the principle of superposition. What do you think that means?
They can combine and try to amplify each other.
Okay, so if let's say you have two beams traveling like that and they meet at a point. This beam has this electric field, this beam has that electric field. How do you sum them? You just sum two vectors. Okay, so to get the electric field at that point, you just sum them. Okay, so that's the principle of superposition. And so if you have multiple beams, you just add one at a time. Okay, the presence of other beams doesn't affect the addition of these two beams. So here are typical numbers for this is a radio wave. This is a 40 megahertz, mega being a million. Okay, what are the FM radio frequencies? So yeah, around 90 to 110. Okay, megahertz. Okay. So that's the window. Yep. So these are, well, they're not FM frequencies, but anyway, the wavelength is about, so this is a typical wave for this frequency. The wavelength is about 8 meters. 8 meters is from here to the wall. Okay, let's say half, yeah, from here to the wall. The maximum value of the electric field, the amplitude of the electric field is about 1,000 volt per meter or 750 Newton per meter. And the magnetic field, you see the strength of the magnetic field is about 1/100 the Earth's magnetic field. Okay. All waves carry energy, so electromagnetic waves also carry energy. All right, so if you shine a beam of light, so let's say you shine a beam of light like this, and you ask how much energy is passing per unit area per unit time. Okay, energy per unit area per time. Okay, so you can stand here and measure how much energy is passing you per unit area per time. That's what this pointing vector gives you. And it's named after Mr. Pointing, and this is 1 over mu naught E cross B. Okay, so intensity is given by that, by Pointing vector. And of course, these are varying sinusoidally, so the intensity is fluctuating. So, but all we're interested in is the average intensity, average of the Pointing vector, which is called the intensity. It's E max B max divided by 2 mu naught. Okay, so when you average them, you get a half amplitude divided by 2. Okay, and intensity is, so a beam of light this long will pass you in 1 second. Okay. This beam will pass you in 1 second. What will be the length of this beam? The length of this beam will be c, 3 times 10 to the 8 meters. Okay? And so that beam will pass you, it's this much energy contained per unit volume. So intensity is the amount of energy contained per unit volume times the length of the beam. Okay? So that's how much energy passes you per second. So the amount of energy contained in the electromagnetic field is 1/2 epsilon naught E square, or B square divided by 2 mu naught. So these are written in terms of E or B because we know that E and B are related in that electromagnetic wave. Okay? So you can express that in terms of either E or B. So the intensity of an electromagnetic beam equals the energy density times C. Okay? Energy density times C. So let's say I fire a bullet. Does a bullet have energy? Kinetic energy. Does it have momentum? It has momentum as well because you hit a dummy and the dummy will fly in the direction of the. Okay? So just like that, a beam of light today we know contains photons, and these photons have energy. Okay, so they must also have momentum. Yeah. And the momentum is given by the energy of the beam divided by the speed of light. Okay, see, remember for your bullet, what was the kinetic energy? What was the formula for the kinetic energy?
1/2 mv squared.
1/2 mv squared. What was the formula for the momentum? mv. So momentum is energy divided by velocity. Okay. So the same thing. For this light beam, the momentum of a beam is the energy contained in the beam divided by c. Now it turns out that if the light beam is reflected, the momentum transferred to the object is twice that amount. Okay, so if a beam is absorbed, this much momentum is transferred to the object. And if the beam is reflected, the energy transferred and the momentum transferred to the object is twice that. Okay. Okay, so a light beam can exert pressure. Okay, so when you transfer momentum to an object, you're applying a force to the object. Okay, so the pressure a beam exerts is the force per unit area. Okay, force is time rate of change of momentum. Okay, and momentum is du. See, momentum is u by c. So dp by dt is du by dt over c. So this is force. Okay. And the rate at which energy is flowing per unit area is the Poynting vector. So the pressure is the Poynting vector divided by c. So this is the pressure exerted by a light beam if the beam is being absorbed. If the beam is being reflected, then the pressure is twice as great. Yeah, so for a perfect reflector, the pressure is 2s over c. Now, so just to give you a feel for it, the force of sunlight falling on the roof of this room. So the sunlight is bouncing off this roof and it's exerting a force. The force is roughly the weight of one of your hairs. You can pull off one of your hair and so what good is that?
space is full.
So, yeah, so we'll come to this in a second. So here, you can actually, so they've actually done this. This is a solar sail. Sunlight is reflecting off this and pushing this sail. Okay, and so you can do a calculation. If you have a solar sail roughly the size of this campus, you know, the campus is Dunn Avenue, International Speedway, White, and that, and Clyde Morris. If you had a sail this big and that weighed as much as a small car, so you have to have a metal sheet, pound it very thin, get it in space, or unfurl it. It'll get from here to the moon in 11 days. Do you guys know how long it took for the Apollo astronauts to get to the moon? Huh? 3 days. Okay, so this solar sail would get there. What's that?
That's still pretty good.
Yep, that's very good. So here's a demonstration of the pressure that light can exert. Okay, you guys know what comets are? What are comets?
They're material from space that's entering the atmosphere and burning up.
Yeah, so they're essentially a ball of dirt and ice. Okay. So, and I was trying to. Okay, so here's the sun, and these comets have highly elliptical orbits like this. Yeah. And when the comets come close to the sun, stuff evaporates. Okay, and now sunlight that's streaming that way will exert a pressure on these particles, and these particles they'll push those particles, and that appears as a tail. Okay. Now it turns out that the sun is of course emitting lots of photons, and it's also emitting charged particles. Okay, so this is called the solar wind, and this is just light. Okay. Now in the comet, this vaporized stuff, there's neutral particles and there's charged particles as well, ionized particles as well. This is called gas, this is called dust. Okay, the dust is blown away by light, and this is blown away by the solar wind. So, what this is showing you is, it's showing you two tails. This is the dust tail that is being blown by photons from the sun. That's pushing this. And these guys are being blown by the solar wind, charged particles, gas tail. Okay, so comets will have two tails. Okay. So again, this is the electromagnetic spectrum, and this shows you, see, these waves that penetrate the atmosphere and that do not penetrate the atmosphere. Okay, so why did we evolve to see in this tiny visible spectrum? Because those waves penetrate the atmosphere. Okay, so it's bright on the atmosphere, on the ground level at these wavelengths. So if we had evolved to see in X-rays like Superman does, on the surface of the Earth, it's pretty dark in X-rays. Okay. We could have evolved to see in radio waves. See, it's pretty bright on the surface on radio waves. But what's the problem with that?
You can only see giant objects.
Very good, my friend. Very good. Okay, so the tinier the object you want to see, the more on the right you have to be. All right. So this is visible light, and red has a wavelength of 700 nanometers. By the way, when you did the experiment yesterday, all, you guys got wavelengths of light at around 530 nanometers, and I looked up the wavelength of that thing, that was right on the money. The wavelength of that green laser was about 530 nanometers. Yeah, so here are the wavelengths, like from 400 to 700 nanometers. That's what our eyes are sensitive to. Shorter wavelengths are called ultraviolet light. Longer wavelengths are infrared light. Okay, here is roughly the sensitivity of your eye. So what this means is, okay, so you're going to shine all these different wavelengths at equal intensity. And your eye responds only this much to these wavelengths and so on. So you see, you're losing sensitivity to UV light and infrared light. Okay. You're most sensitive to blue-green light, green-yellow light. And that's why the color of the tennis balls. So you can, different wavelengths appear as different shades, and you can see 7 million shades. Yeah. So this device of hers renders about 16 million shades. So they sold you a bag of goods. So you can see only 7 million shades.
Some people can see more,
Yeah, some people can see more. What's that?
which is fascinating.
Yeah. Yeah, but every sense we have a wide range. Some people have good tonal quality and stuff like that.
Really cool.
We talked about this. What is this?
Water.
It's a water molecule which has a dipole moment. Okay, so remember the negative oxygen are greedy for electrons. So here is the center of negative charge. Here is the center of positive charge for the water molecule. Okay, so if you have a dipole like that, and if you put it in an electric field, the positive charge feels a force in this direction. The negative charge feels a force in that direction. Okay, so here is the dipole moment. What the electric field does is it's trying to turn the dipole and line it up with the electric field. Okay, so if this is a dipole, if this is a water molecule, and you have an electric field like that, it tries to turn it like that. And then if you switch the electric field like that, it'll switch like that. Okay. So that's what a microwave does. It switches this electric field 5 billion times. So that electric field in the microwave grabs hold of the water molecule and jiggles it like this. So you want to grab hold of something using an electric field, it has to have a dipole moment, and you can grab hold of it and jiggle it. And you heat the water molecule, and then the water molecule shares the heat with everything around it.
It's kind of hard to comprehend how much it's reversing direction with only a second. 5 million times in a second.
5 billion times.
5 billion times in a
Mm.
second.
Yeah. Well, the frequency of visible light is about 10 to the 15 hertz. The electric field is switching 1,000 trillion times a second. It's oscillating 1,000 trillion times a second. Yeah. We have a hard time comprehending that because, the masses we deal with are so large that, So here's how a radio station works. Okay. Yeah. So here's the oscillator because of the resistance. So let's say, and the 89.9 megahertz station, so this is oscillating at that frequency. Okay. This is oscillating at that, and the natural frequency of this also is there's the inductor, there's the capacitor is also 89.9 megahertz. So you feed energy here, which is coupled there, and this is an antenna that'll radiate away the energy. So again, remember, to radiate energy, what is it that you need to do? To radiate electromagnetic waves, what is it that you need to do? You need to accelerate a charge. And that's what was happening. Okay. So, all right. So this is called a dipole antenna, and electromagnetic waves are produced by accelerating charges. So this is a shortwave radio. Okay. A dipole antenna is made of two rods. Those are the two rods connected to an oscillating source. The length of each rod is equal to 1/4 of the wavelength to be emitted. So this is the length of this rod is lambda by 4. Okay, so you learn that all in antenna theory, okay, if you're interested in it. The magnetic fields are concentric circles. So if this is the dipole antenna, the electric field is oscillating like that, parallel to, and the magnetic fields are oscillating like this. So you guys might have seen, well, again, this is before some of your time, but in the old days you would have TV antennas, and if you're catching the electric field, you have dipole antennas like that. And if you want to catch the magnetic field, you have rings. Okay, metal rings, and the metal rings have to. So if you want to catch the Orlando station, the metal ring has to be like that. The plane of the ring has to point to the station. Okay. So the intensity of if here's a radio station, the intensity is maximum like that. So if you hover over in a chopper over the station, you don't have any signal. What is AM and FM radio?
Amplitude modified, frequency modified.
Amplitude modulation,
Modulation.
frequency modulation. Okay. So here's what goes on. So here's the carrier signal. The green is the carrier signal, and the blue is the message. Okay. So what you do is the carrier signal has a much higher frequency than the message. Okay. So you combine the carrier signal and the message, and you see the amplitude of the message of the carrier signal is being changed. And that is amplitude modulation. Okay. The good thing about this is this will travel a long distance. The bad thing about it is there's other random noises that have similar effects to these guys. So they have long range, except that you have noise associated with that. With frequency modulation, okay, so what you're doing is there's a carrier signal, and what you do is you break up this message into little bits, and you do Fourier transform, and you change the frequency of the carrier signal. You see, the amplitude of the carrier signal is the same, its frequency is shifted. That's how you encode the information. Okay. Now this has the advantage that noise won't bother it. Okay, it's very hard for noise to replicate that. But the negative is doesn't have long range. Okay. So the range is good on that, and noise is a problem. Range is bad on that, but noise is not a problem.
I think we recall on Physics 1 mentioning that one of the signals could get like signals from like across the country at some point.
Yeah, shortwave radio amplitude model. It reflects off ionospheres.
And then so you can bounce the signal off
No.
the
Ionosphere, yeah.
Yeah.
So that's what ham radio people do. That's how come they can get signals from Australia to the US. All right, guys, so that's it for the lecture.